Okay, so I'm sorry about last week. I'm still carrying a cold, but much better than last week. I may still cough today. I hope I can cover for the entire course. Today I want to show you something you may not learn from other professors. It's a research direction that is related to my PhD dissertation. So in other optimization courses, they usually don't talk about this. So let me, okay. Screen. So today is May 20th. I would like to show you a kind of optimization problems with uncertainty. So what's going on with uncertainty? So let's say we have a problem minimizing f of x subject to, let's say, g of x. Let's just give an example, x squared. And let's say our g is x must be larger than 3. So x larger than 3. 3 minus x must be smaller than 0, right? So if I have a problem like this, and when I make a drawing of the functions, my auxiliary function looks like this. This is my f, and here's 3. So there's a wall, right? And obviously, the solution is right here. X equals to 3. That is the solution that satisfies the constraint, and also having the minimum function value within the feasible space. However, if I tell you, and this happens in reality, if I now tell you x is uncertain, what does it mean by uncertain? X, there are some, I should say, there will be unexpected or expected variance in the value of x. And sometimes we can describe this kind of uncertain behavior by a distribution. So let's say x is normally distributed. Okay? So what does that mean? That means x could be having a mean value and a standard deviation. So sometimes we write in this way. This represents normal distribution. This is the mean. And this is standard deviation. Okay? Sometimes people will put square right here. Sometimes. It depends. So you need to define your notation clearly. If you put sigma square over there, then it's variation. Okay? Standard deviation squared equals to variation. So that's why sometimes people will put variation in the second spot of this notation. So if I have a normal distribution with a mean value and a standard deviation, what does it mean? That means sometimes people will say x is equals to a mean value plus or minus the standard deviation. So it's like within a range, okay? And if you make a drawing of the distribution, this is x, and this is where the mean is, okay? Then the probability of x lies in this distribution. And here is sigma x, okay? So if this is happening, if you are dealing with this kind of variable, what's gonna happen is, in your original problem, this is where your x is, and you try to draw a distribution of your x right there. You realize 50% of the chances your x is gonna be smaller than positive 3. So that is violating the constraint. So we call this failure rate. You have a 50% of the chances that you will fail. So if this is a real problem, x could be the dimension of a part. Let's say you are using a machine manufacturing a metal plate in the length of x. Are you able to guarantee the length of every part be the same all the time? You cannot, because even for manufacturing, precise manufacturing, there's a tolerance. In your engineering drawing, you allow some tolerance. So every dimension in a manufactured part has a allowed value or expected value, plus or minus some tolerance. So for quality control, as long as your part is within this allowable range, that's an okay part. So the designer needs to figure out if this is a dimension, how much tolerance do I allow? Can it be a little bit larger or smaller? So in reality, tolerance exists everywhere. This is basically this due to uncertainty, because you cannot control uncertainty. It happens by random. So if you have a design variable that is really critical, and when you solve optimization and you figure out, okay, x equal to 3 is the optimal, it cannot be 2.999. It has to be 3 or 3.0001. In that case, any value that is smaller than 3 will be value. So whatever we have learned in the past, never talk about this. And if you apply this, if you apply traditional optimization to real life, you may see issues like this, because you never consider uncertainty in real life, in math. So how do we deal with this? If you can figure out the standard deviation of a variable, then can you control the failure rate? So the goal of today's lecture is to control this. So one way to resolve this issue is to have, let's say here is x equals to 3. This is smaller than 3. This is larger than 3, right? And if I can have my design point right here, maybe this is my mu of x, and I have a standard deviation like this, okay? Then the failure rate will be low. It's much lower, okay? So probably I can figure out a way to shift my design variable toward the feasible space by a certain distance. So I can control the failure rate at the tail. We sometimes call this tail of the distribution. We can control the area at the tail of the distribution within the failure region. This is a failure region or infeasible space, right? But the question is, how much should we move? If I move toward right too much, then I will be further away from the optimality. The optimal, suppose, is to be equals to 3, right? I want the objective function to be lower. But if I move toward right too much, my objective function become greater. So I have poorer performance. So when you are too safe, then your performance becomes poor. Right? If you move right, when you move right, you will be safer, but poor performance. Performance depends on how well your objective function is. So you won't have smaller function value. But if on the other side, if you move left, of course you can have better performance, but the risk is higher because the tail of the distribution has a greater area when you move left. So we want to stay at the position that is having the exact probability of failure. Then you have a expected failure rate. You know, maybe the failure rate is 1%. So when you produce 100 pieces, 1 piece will be failed. Then you only have 1 unlucky customer. He will complain. You maybe will fix the part for him, or give him a new one, or pay him back. So the loss will be just 1%. Right? Business-wise, you can control your business. But if you cannot control this, you still stick with the optimal solution at x equals to 3, then you have 50% of failure. So when you make 100 pieces, if you are by statistics, 50% of the parts will be failed. So if you make money for 50 parts, but you lose money for 50 parts, that's definitely not acceptable. So you definitely want to stay safer. But if you choose to become so safe, your failure rate is less than 1%, maybe 0.01%. So when you make 100, none of them fail. They are all parts that satisfy the constraint, but they have poor performance. So it's like you are making a car, you build a car so heavy, so it's so safe, your car will not, when there's a car crash, the person inside will be so safe because your car is so strong, nobody can crash the car. But since your car is so heavy, so when you speed up, the speeding performance is poor because you have a heavy inertia, right? So there's always a trade-off. If you want to drive faster, you want a lighter vehicle. But when the structure is lighter, it's weaker, it's more dangerous. So performance and safety usually is a trade-off. They are fighting against each other. Okay, now how do we deal with this? So one way to deal with this is to transform the design space to standard normal design space. Okay, so what's going on? So if I call the original design space as a capital X, from now on, when I have capitalized character, that means a variable with uncertainty. So in fact, I should write it this way. So this is a normally distributed variable. Okay, so I use capitalized X to represent the entire distribution. So when you convert everything into the standard normal space, we use capitalized U as the standard normal design space. So there's a relationship between them. U equals to X minus mu divided by standard normal, standard deviation. That's how you can transform your design space to the standard normal space. So since the distribution can be transformed in this way, any value inside those spaces can be transformed from one to the other using the same equation. So small case variables also can also use this equation. So what's the difference between the capitalized character and the small case character? So the small case one is a value. So this is an original space. If I pick a position, okay, here, if I say this is X equals to 7, some value right there, it's just one value. That value can be also transformed into the standard normal space. When you do that, you get a new number, but just an individual value. Okay, it's like a one-to-one mapping. But what is the capitalized one? So the capitalized one is the entire distribution. So like this whole thing is the capital X. The whole distribution is being mapped to the standard normal space. So when you have a capitalized one, it's a distribution. Okay. So I just want you to know you can transform from one space to another space. Now, in order to truly figure out what's going on, let's apply some numbers to the problem so we can physically see what's going on. So let's say we are solving, minimizing, we have, for the adjoint function, I think we will just use the mu x squared, okay? So for the adjoint function, we don't care about the distribution. I just want the mean value. I want the mean value squared to be the smallest. Okay? But for the constraint, what's going on is now I want the probability of the failure event. So what is the failure event? So the feasible event, I should say safe event. So the safe event is 3 minus x smaller than 0, right? So the failed event, it would be the opposite. So when you have this, then this is the failed event. So now we will say 3 minus x, but here I'm using the capital X, smaller than 0. This is basically the failed event. Okay. And as x is the normal distribution, okay? Okay? So I want this basically this whole thing. This whole thing basically is the failure rate. Failure rate, right? I want this failure rate to be controlled. So I can say I want this to have 1%. So I can say this is like a allowable failure rate. I allow only 1% of failure. 2% is not good. 0.9% is okay. 1.1% is not good. So I want this failure rate to be within 1%. So how do we do that? So now I want to convert the whole thing into the standard normal space by what I introduced you above. So over here, what's happening is you can have an equation like this. X equals to mu plus capital U, right? You get something like that. So you can apply that into the equation right here. So you will see something like this. 3 minus, I need to define. So let's say X is a normal distribution. Let's say mean value can be changing because we move our design variable by the optimization process. We can change the position of the mean, but let's say the standard deviation is a constant value. So it's always having a standard deviation of a certain value. Let's say it's a 1.5, okay? So over here, mean is still the mean, right? And let me see. So I guess I need an initial guess. So I can put a number in there. So let's say my initial guess, so k equals to 0. My initial guess is 5, okay? So initially, it's a normal distribution, 5, 1.5, something like this, okay? So initially, my constraint looks like this, 1.5 plus u times 1.5 greater than 0. And this has to be smaller than 1%. Okay? So let's work on the left-hand, what's inside the bracket. So now we will have so negative 7.5 u, that is larger than negative 3, right? And I can change this to u smaller than, so 3 divided by 7.3, 0.4, okay? So, it's something called the probability of standard normal design variable u that is smaller than 0.4. So what is u? Now I want to show you something that you might know. Or you may not. So there's something called the standard normal distribution table. There's a table. Let's see if we have a good quality for this. You can easily find this on the internet. No, I don't. Maybe about this one. Okay, there's a standard normal table. Okay. Let's see if this one, the quality is not very good. I want to find a better one. Let's see if this one is better. Okay. Okay, here. I hope it's clear enough. So, if you Google for this kind of table, standard normal table, okay? And usually it has a drawing, okay? And usually there's something either called Z or U, okay? And it shows you maybe there's a small case Z or small case U right here. And it will put a color on one side of the distribution. So what does this color represent? The color means integral from negative infinity to that specific position z, and there's a function right here. It's called a f of, I think I actually like u better. I like u better. So maybe in my case, I will just use, but it's misusing Okay, I will use the terminology I like. Let's say this position is U0, okay? So this is U0 and DU, okay? So this is already in the standard normal distribution. And whatever position U0, it could be any position. And this table will give you the calculation of this integral. Basically computing the area from negative infinity to this particular U0 and counting the area underneath the distribution. So I can tell you, if you do this, if you do the integral from negative infinity to infinity, this equals to 1. Because 100%. Any question? I'm sorry. I didn't do this. Next time, just speak up. Scream. Okay. So let me mention this again. Whenever you see a standard normal table, usually see a drawing like this. Because sometimes they draw this on the opposite side, on the right hand side. So every table has its own way to represent the distribution under the area or percentage underneath the distribution. So when you see a table like this or a drawing like this, and there's like a cutoff position U0. I like to use U. So the area is an integral from negative infinity to this particular position U0, and you do an integral of it. And if you do an integral from negative infinity to infinity, basically you are computing the area completely underneath the entire distribution. It's gonna be 1. So for every statistical distribution, it's kind of it's representing the distribution or probability of certain event. So overall, the entire probability should be 100%, right? And if you are just saying, if you choose a cutoff and say, okay, what is the probability from negative infinity to certain position? This table tells you what's the value. So you don't need to calculate it by yourself. So in the table, usually what's going on is it will give you values of U0, and usually it's like this. I think let me double check. Yeah, usually it will give you 1-digit accuracy for the column. So something like this, okay, and for the columns on the right, it will give you a second digit accuracy. So something like this, okay, and it will give you some number inside. So if you have 0.1 from the left, 0.2 on the top, that means this is trying to compute 0.12. So U0 is 0.12. It's trying to compute this. Okay? So whatever number is giving you represent the percentage underneath the distribution, right at the cutoff position, 0.12. And since this table is choosing positive U0, all these numbers are supposed to be greater than 0.5. Make sense? Because they are positive. Here is 0. Here is u equals to 0. So if this table is giving you all kinds of positive u zeros, then you are actually computing area greater than 50%. The entire left-hand side, this is 50%. So if you are analyzing somewhere right here, so it's gonna be 50% plus some additional area right here. So it's gonna be some value greater than 50%. Let's check on this. So from here you can see if z is 0, that means it's 50%. And over here you can see they're all values greater than 50%. But how about if you are computing something on the left? What do? You just need to flip it, because this normal distribution is symmetric. So if you want to compute something like this, let me show you. If you want to actually do this, here is 0, and u0 equals to -2. So you are computing this area. What you can do is,
这是我在网络上找到的 What you can do 相关结果，请看。
shut up. Okay. So what you can do is, the area, if I call this A is gonna equals to 1 minus from negative infinity to positive 2. Why? Because when you are doing this, you are actually doing, this is 0, here is 2. Right? So this, whatever on the right, can be determined from the table. So you just need to compute the greater half and use 1 to minus the result you have. Okay? So sometimes we will define this as a capital F and U0. So this is capital F 0.12. This is basically 1 minus capital F 2. So what is small f and capital F? Okay, so small f, this is basically so-called probability density function. So for the PDF. And the entire distribution is the PDF. Okay, that's why you use it inside the integral, but you don't, or the f itself is the whole distribution. Okay, but when you have this integral, you are computing the area from negative infinity to certain position. We define this as capital F and U0. Okay, so the area underneath within the range, we call it capital F. So this is actually the integral from negative F to U0 and F of U du. And we call this cumulative distribution function. Distribution function. So-called a CDF. So in statistics, PDF and CDF. Okay? So, back to what we had. Now I am trying to compute this. I have a, let me see. Am I doing this right? I'm just trying to figure out, am I doing this right? Let me make a drawing, just to make sure. Here's 3, here's my wall, and here's 5. Here's my distribution. So, I made a mistake right here. This should be negative, so I'm sorry. That's why it's weird. Here, this is negative. I made a mistake. Because the equation is here, okay? So if that's negative, and I must be sick again. I did everything wrong in the math. So this is negative 1.5, and this is negative 2, so this is positive 2. Okay. Okay. 2 divided by 1.5. Okay, so this is negative 1.33. Okay. I didn't know how I made those mistakes. 2 divided by 1.5. Okay. Okay. This proves that I'm still sick. Okay, now this is making sense. If I'm trying to compute probability of u smaller than negative 1.33, that means I am in a standard normal space, and here is u equals to 0. I have a standard normal distribution, and I choose a position, it's like a u0 equals to negative 133. So I'm trying to compute this. So whatever I said within the underline can be done by doing the calculation on the last drawing. Make sense? I'm trying to compute the area where this is my whole distribution, right? My whole distribution, whatever that is smaller than negative 1.33, I need to know the area of that. So in fact, you are computing, this is the CDF of negative 133. You're actually doing this. But in the table that we know, we cannot do negative u0. So what you can do is 1 minus f, 1.33. So we can flip it. So here is 1.33. You can use a table, and you use 1 to minus the large area that is on the left of 1.33. Okay, so let's go to the table and find when here's 1.3. 1.33 is here, so 0.9082. 0.9082. Okay? So the table tells me this is 1 minus 0.9082. So this is actually So it's actually 9%, 9.18%. Is it smaller than 1%? No. So my current design 5 is not safe enough. The allowable failure rate is 1%. So you can say allowable reliability is 99%. So far, if my design variable is 5, my safety level is 19.82%. It's not good enough yet. So you need to move your variable right a little bit. So you keep on changing your mean value until there is a position where your failure rate is exactly 1%, then you stop. That's the goal of optimization with uncertainty. So if you are dealing with normal distribution, this is doable because you have this table to figure out. But if one day you cannot figure out what's the distribution of your uncertainty, then it's really troublesome. Because if you go back to the original problem, we can convert this to standard normal because I assume it's a normal distribution. But without enough experiments, how do you know this uncertain variable is normally distributed? So usually it's a guess, unless you have enough resources to do experiments. So what if you are not lucky? It's not normally distributed. Then you are dealing with a very troublesome issue. So let's talk about non-normal distribution. So let's say here's my x, and my objective function is like this, and here's x equal to 3. So now, if I'm dealing with a design variable which is normally distributed, right? So the goal is to make sure this is only 1%. Then that would be my optimal. This is the problem that has normally distributed uncertainty. But when you have non-normal distribution, what's going to happen? So let's say you have a distribution that looks slightly different. How about this? No. Yeah. Because normal distribution is symmetric. Both sides are the same. But if you have a distribution like this, then you don't have a table, like a standard normal table, to evaluate the failure region. Right? So if you cannot compute this area, then it's difficult for you to find out where you should move your mean point. So since you cannot evaluate the tail, then it's hard for you to determine, okay, where should I select my optimal position. So the failure region is 1%. Then it's hard. So get back to the formulation. So this is the formulation. What's difficult is it's hard for you to evaluate this failure rate. It's hard for. So of course, you can do it by the hard way. How do you do it by the hard way? This equals to from negative infinity to actually to 3, and you can do this. If you call this the PDF in the X space, and of course we don't like to use the F again. Maybe I just call it F prime, okay? So if I call this F prime, so not the objective function, but actually this is the PDF probability density function in the original space. Since you have no idea what kind of distribution it is, you cannot convert to the standard normal space, because you have no idea what kind of distribution it is. But if you know the distribution exists, you can truly do integral. You can truly do this, but it's going to be very costly. So it's like you need to sample a lot of X and figure out how it's gonna distribute it. So it's like in reality, you are making a product. You may need to produce 10,000 pieces, and then do measurement on all of them to figure out how those critical dimensions is going to be distributed. Then you can figure out, oh, when I make 10,000 pieces, the resultant dimension distribute like this. So when I decide, okay, my dimension now is 5, let's say mu is 5. Okay, the distribution looks like that. Oh, I realize 2% of the dimension is less than 3. By real experiments, you can truly compute. It's like a true counting. So in my PhD work, we want to tell people, don't do this. If you truly make a great amount of experiments and try to count the percentage of failure, it's not very effective. So my PhD work is trying to figure out ways to make this more effective. Unfortunately, no matter what method we work on, if you have no knowledge about the distribution, it's almost unsolvable. So you still need some statistical data. Many of you are doing projects with experiments. So whoever is working on experiments, all of your experimental data has uncertainty like this. How do you know? How do I know? If you repeat your experiment 3 times, they give you different results. That means your experiment definitely has uncertainty. Sometimes maybe the way you perform the experiment is slightly different. That tiny difference will produce slight difference in results. So if you truly want to figure out the distribution of the results, then you need to perform a lot of experiments. And one day you realize, oh, the performance has a mathematical relationship with your variables, but there's uncertainty. Okay, so it's a very very challenging research field. If you want to deal with design with uncertainty, it's always very challenging. Okay. So anyway, I don't want to, because I only have one lecture for this, I cannot cover everything from my PhD work. So I'm gonna show you something only within standard the normal distribution. Because from what I have shown you, we haven't seen how we can iterate. We only know how we can evaluate the failure rate. If the design is too safe or not safe, we only know how safe it is, but we haven't known how to iterate. Sorry. So let me now get back to normally distributed problems. And let me show you how we can iterate in optimization problems with uncertainty, but only one-dimensional problem. So here, probability of failure event, right? So failure event should be this. So now I'm formulating this in a more general way. So basically, this is the failed event, right? So you know the safe event is g of x smaller than 0. So originally you want this, but when we talk about when we are controlling the failure rate, we basically want the overall failure rate to be smaller than or equals to the so-called the allowable failure. Right, so this is a more general way to formulate this. I'm sorry. Okay, so what I'm going to do right now is a method called first order reliability method, so-called the form. Okay. How do you do form? Basically, we're going to linearly approximate the constraint. So first order Taylor expansion. Here you will have G equals to the expansion point. So maybe I can do expansion at the we don't choose the expansion point yet. So let me just say G0. So some expansion point. So this is some expansion point. Okay? And then continuing with this, your x is gonna be uncertain, minus your expansion point, and this is your gradient, right? So what happened was, I just did first order Taylor expansion of this guy. At the end, I have this. The first order Taylor expansion. So this we only deal with the left hand side so far. And then you can kind of reformulate this as x must be, do we plug in yet? Maybe we, maybe we let me see what do I do. I think I should transform to the status normal space first. Do I do that? Yeah, I should do that. I'm sorry. I should get rid of this. My mistake. Delete. Okay. So first, transform to the U space. Okay. So what you will get at the end would be a new function. You will get a new function. So at the end, it's gonna be like this. I think yes. New function. So from here, basically you apply U equals to capital X minus mu. After you plug in, at the end it's a new function. It's but expressed in capital U. So then you are going to do first order Taylor expansion at some expansion point. So I'm going to call this expansion point U. Do I use U0? Let me call this U1, okay? Just a number. So if I do that, I will have G U1 in the U space plus U minus U1 gradient. 1D problem, so G prime. Basically G prime of U1. It's a 1D problem. So at the end, I would have U greater than, smaller than actually. Let me try not to jump steps. Greater, yeah, okay. Don't jump steps. Minus GU1 plus minus GU1 plus U1 times G prime of U1. Okay. So P U greater than negative GU1 plus U1 G prime of U1 divided by G prime of U1. Okay. So we can compute something like this. Okay. So if I choose a point for my expansion, a very unique point, I choose U1 at so-called most probable failure point, so-called the MPFP, or sometimes people don't put value. Sometimes people just call this MPP point. And people would like to use U star to represent the MPP point. There's a reason, but I'm gonna tell you why. So what is the most probable failure point? So in the original problem, here is x equals to 0, right? We have x equals to 3, and this is where maybe my mu x is, let's say 5, right? And I had standard deviation 1.5. That's what we have. So after converting everything to the standard normal space, actually in the U space, this is where U equals to 0. If you figure out. And then over here, this is where U equals to some number. So U, this is U equals to, U equals to x minus mu x divided by standard deviation. So this is 3 minus 5 divided by 1.5. So 3 minus 5, negative 2. So 2 divided by 1.5. Okay, so negative 1.33. We had this earlier. Okay? So we usually call this point the MPP. Why? Because that's right on the constraint. So that's the position where we have it's like most likely we are about to fail. So we like to choose that one as the MPP. So in our case, this is our U star. Okay? So if we do that, and if we plug in this problem, you will realize something. G of U equals to negative 1333 actually is 0. Because this is the constraint where we have constraint value equals to 0, right? So if you evaluate this right on the position where you have the constraint value equals to 0, it's gonna be 0. So at the end, it's going to be U larger than U star G prom U star G prom U star. You don't really, because G of U star equals to 0. So what you need to do is to compute the gradient at the U star. So what is our G? Our G of x, originally G of x equals to 3 minus x, right? We want this to be smaller than 0. So this is our G. So when we convert to U, what do we convert? U equals to capital X minus mean value 5 divided 1.5. So G of U, capital U, if I use capitalized one, equals to 3 minus, over here, capital X equals to 5 plus 1.5 U. So 5 plus 1.5 U. So this is in fact is negative 1.5 U negative minus 2. So if you plug in negative 1.333, G equals to 0, right? So this is my G. How about G prime of U? G prime of U. So basically derivative. So 1.1, negative 1.5. That's it. So I can plug in to what we had earlier on the top. P U larger than negative 1.5. Sorry. U star. U star is negative 1.33. And here is 1.5 and divided by negative 1.5. So at the end, still, U larger than negative, positive or negative? Positive. Is it? Failure rate. Oh yes, correct. 1 point. But that doesn't help us. That doesn't help us. That's the same thing. How can we iterate? Let me see. That's not how we iterate. So I just derived the whole thing again by a general equation. I just derived this in a general math. But is it correct? P probability of, it was smaller than 1.33. Let's see. The sign, sign screw up. I screw up the sign. When because the G is negative. So when I divided the right hand side by G, this becomes negative actually. So the problem really depends on the sign of G. In this case, G prime is negative. So I will have negative sign here. In this case, negative. Right, so I just show the same thing, but with exact same math. But symbolic math. I think this is not how I would like to. That doesn't help us. That doesn't help us. So I should let me see what I should do. I think I get this. This is capital U. This is capital U. So it's capital U. Not small. So at the end, we have a general equation like this. Capital U smaller than U star times G prime U star divided by G prime U star. Smaller than PF. Okay. In this case, G prime of U star negative. Okay? So I guess we still have to do something. Okay, this equals to so-called CDF of the limit point, right? Because these two cross out, so just use star. Just use star. Right? These two cross out. So remember when we introduce, let me see where, here. The probability of u smaller than something equals to the CDF of that value. Sorry. Right? So I'm just showing you the same thing. Yeah. Right? CDF. So we can we have a form like this. So what we can do next is something very strange for you, I think. The inverse of the CDF, smaller than. It would be a little weird, but I will let you know how to compute this. So we are going to again perform first order Taylor expansion. So we will have now I think we can use the current design plus unknown u, actually k plus 1, that's fine. And u star prime. Maybe I will just say du star du. Yeah, if you can compute that. Yeah. So what's going on is, this is where we can iterate. This is how we can iterate, because for your current design, this is your current design. And actually, when you do this, because you are transforming everything to standard normal space, so in fact, you are transforming based on your current design. So your UK would be 0 actually. So this is actually also 0. And this is your next design. So your next design is right there, and this equation allows you to figure out what is your next design. So now you will have a expression and inequality constraint with your unknown, your next design. So it's a new expression with inequality sign here, and you have a unknown variable. So with all these, we just transform probabilistic expression to a so-called deterministic expression. So originally, it was a probabilistic expression. Now you convert to so-called deterministic expression. So what is probabilistic expression? It's like a probability of a failed event must be smaller than some probability. And like I said earlier, sometimes it's difficult to compute probability. But in a deterministic expression, basically is a function of some variable smaller than some limit. Something like this. So it's an equation that you can use it in optimization. By all these conversion, you can get this. Okay, so the only issue is how do you compute this? How do you do this? Okay? So basically, it's like now you have a allowable failure, failure probability. For example, if you are looking for 1% of failure rate, that means the reliability is 0.99. So 0.99 is right somewhere right here. So it's 2.33. 2.33 is, if you do this, this is almost 90%. This is U, and here is 2.33. So, sorry. .33. So from the table, if you're looking for, was it 19%? 92.33, 1%. So 99%. 99%. If you are looking for exactly 99% of safety, so U is 2.33. So actually this value is 2.33. No, not 2.33. Should be negative. So because we said this is 1%, right? So we are looking for F inverse of 1%. So F inverse of 1%, basically, if you have negative 2.33, then on the left-hand side, this is 1%. So in fact, this will be negative 2.33. That's how you inverse it. Because if you perform forward CDF, you put U value in, you get probability back. But if you inverse it, you put probability in, you get U0 back. So in fact, you are trying to find a design that has so-called a U, some U star that is smaller than negative 2.33. Okay. It's hard for me to do programming today because this is very, very complicated. And I'm not sure if you're interested in optimization with uncertainty. I just want you to know this kind of problem exists in the world. And sometimes we call this system reliability. Okay. So, or this kind of optimization problem, we call this a reliability-based design optimization. Okay, so we call this RBDO. Okay, when I first came back to Taiwan in 2012, so it's already 12 years ago. I wanted my student to work on RBDO because that was what I did when I was a PhD. So 12 years passed. Only one student, one master student understand RBDO. So I taught how many graduate students? Let's see. Let me see how many graduate students I had. Starting from the, okay. I had 53, more than 50 graduate students. Only one graduate student worked on RBDO. So it's very, very complicated math. So it's hard for me to write down a code right here in the class. From scratch. It's very complicated. But I just want to show you there is this kind of research. I still have some time. I'm going to show you the presentation file for my PhD, and you can kind of use it to I hope use it to learn more about RBDO. Okay, let me see. So this is my presentation file. Where is it? Ah, here. My review. Or we can just let me see which one. Okay. Ah. No. Home point. Where did I keep that? Okay. Okay, moment. So this was 2009. How many years ago? Yeah. So 15 years ago? Yeah, so this is bullshit. Don't worry about what's going on. Okay, starting from here. So if you have a linear problem like this, and the colors are representing different constraints. And from here you can already see there's a triangular area that is the feasible region. And the dashed lines are the contour of the ability function. Lower the better. So blue color right here at the left lower corner is representing lower function value. Red is higher. So from here you can tell this corner point is the optimal if you have no uncertainty. But if there's uncertainty of the variable, here I am showing you some kind of elliptical shape, because this is a 2D problem. If you have normal distribution in x1 and also normal distribution in x2, and if you try to view from the top, that dome shape is like an ellipse. And if you want to see the concentrated area within the shape with certain percentage, the size of the shape changes. The reason why I'm choosing 98% and 99.87% is because later on, I am creating allowable failure rate of 2% and 0.13%, two different levels, two different safety levels. And the reason why when we view from the top and we don't see circular region is because the x1 and x2 are drawn in a different scale. Did you see a different scale? Right here, for B, this is 10. But for A, this is already 20. So they are drawn in a different scale. That's why when you try to draw the distribution, it's elliptical. It's not like a circle. But suppose if you have same standard deviation for A and B, and when you try to draw the distribution, it's like a circle. So actually, these two are circles. Okay. So what's next? If you analyze the uncertainty at the optimal solution that you had earlier, you have 50% of failure rate for G1. You have 50% of failure rate for G3. You're okay with G2 because G2 is far away. So you are 100% safe for G2. However, 50% failure rate for G1, 50% for G3. So it's very bad. Overall, your overall failure rate is more than 90%. It's around 90%. So this is a very bad design if this is what you're truly making. So the goal is, if I have a so-called a probabilistic optimization, here, all these are the fail event. These are the safe event. These are the fail event. If I allow only 0.13% for the failure event of G1, 0.13% for the fail event of G2, and here the tricky part is I choose a different allowable failure rate. This is a 2% for G3. Then I actually need some new constraint which is shifted inward toward the feasible space, a smaller space. I actually need that. And if you use that smaller feasible space to find the optimal point here, you will see the greater ellipse is tangent to the original G1. So the origin, the greater ellipse is representing the area of 99.87%. So what's outside is 0.13%, exactly matching the allowable failure rate. And if you look at the smaller ellipse, it's tangent to the original G3. So the smaller area is representing 98% of this uncertain variable. So what's outside of the ellipse is 2%. And it's now, if it's tangent to this original G3, that means it's matching its allowable failure probability. So the goal of this research is to find those shifted constraints that gives you a smaller feasible space but have good control of your allowable failure rate. So that was my PhD work. Okay. So like I said, the failure rate of G1 could be 0.13% and the failure rate of G3 could be 2%, exactly matching the goal. And how did I do this? Here. This is what I have written on the iPad. And like I said, traditionally you need integrals. And when I work on this on the iPad, it was a 1D problem, but for a multi-dimensional problem, it's gonna be multi-dimensional integral. It's very troublesome. So here, whenever in the future when you see this, this is actually the capital F that I mentioned. This is called capital Phi. Capital Phi is actually, if this is U0, it's actually the capital F that I mentioned. So it's actually the integral from negative infinity to the U0. And over here inside, they use the small phi of U. So the reason why they want to use phi and capital Phi is because they want to use capital F for original space. Here should be X. So this will be PDF in the X space. This will be CDF in the X space. And they want to keep this as the PDF in the U space. And this will be the CDF in the U space. They want to make a difference between the original space and the standard normal space. So that's why you will see something like this. That's the CDF in the standard normal space. So how come there's something called beta? What's beta? Beta is actually the reliability index. So where's beta? So what is it? So if you have here's u equals to 0, and here, let's say -3. Okay, so they call this beta. The distance away from the failure region. They call this like the space between this is your current design, right? And this is the fail. It's like the wall of the Actually, we call this limit state. Limit state of the failed region. So the distance between the current design and the limit state in the U space is called the reliability index. Okay? So how come 3? Because sometimes we call this 3 sigma. Have you heard of 3 sigma design? In the standard normal space, you want to keep distance away from the failure and having a safe region in the scale of 3 sigma, 3 times of your standard deviation. So if your design, this is your x, and here is 1 sigma, 2 sigma, and 3 sigma. So you only allow this amount of failure, then your design probably will be 99.87% safe. And here is 0.13% fail. So 3 sigma designs. Why do I know? Because I use this all the time. And there are people do 6 sigma. That means they want to keep away from the failure with a distance in 6 times of your sigma. So the failure rate will be super low. The reliability will be 99.99%. Okay, so over here, beta. Yeah. Beta is how much you keep away from the failure region, the allowable one. So over here in my PhD work, same math I showed you earlier, right? X minus mu divided by standard deviation, how you transform to the standard normal space. Over here is a tricky thing, so-called MPP, right? I told you we need to determine MPP. But it was a 1D problem. It's easy to know where is the most probable failure point. So earlier I said, in your problem, if this is your constraint, x equals to 3, and here's your design. We choose this one as our MPP, right? Because we want to determine perform some first order reliability method right at this limit point. But if we are dealing with 2D problems, let's say this is a 2D problem, okay, and I have a constraint, let's say this is g of x1 and x2 equals to 0, and here is my design point with some uncertainty. So this is the PDF of the design variable. So there's a shape. So what's happening is when you move toward the failure region, this distribution moves with you. So here's a point. That's the most likely point that will lead to failure. So we're looking for that particular point. So we have to transform to the U space. After we transform to the U space, the random distribution becomes circular. So even it's elliptical in the original space, in the U space, this is U1, U2, and sigma now equals to 1 after you transform. The new center is right at your design point. And this linear equation will be transformed to a certain new function. So this is g of x, and this will be g of u. So what's happening is you're trying to find this point, the perpendicular point right there.
So this will be so-called the most probable point. It's like you have a circle, you're moving toward your constraint. The first tangent point is going to be the most probable. And in this math, we're trying to find some point on G, and that is having the shortest distance. Shortest distance. So solve this problem. The solution will be this point. So that's why people solve this. But in my PhD work, we realize there's an issue. So we reformulate this whole thing in a certain way. This is actually exactly what I said, how you convert probabilistic constraint into deterministic constraint. Anyway, and later on I will tell you there will be some issues. No, I won't tell you. I mean, I will show you there are some issues, like this. Sometimes this method leads to incorrect solution. Okay. So in my PhD work, I modified the formulation into a certain form. It's a lot of work to explain. So that's a new expression. We were supposed, actually, if you look at this is just like what I show you in my note. I said U star times G prom divided by G prom, right? That's what I said. Of course, there's a negative sign over there, but it doesn't matter. This is the multi-dimensional form. With this, at the end, you will have a expression. This is exactly what I show you. You estimate basically the reliability index. In my note, I said U star, but in one dimensional, U star is beta. But in two dimensional, this distance is beta. But in my formulation, you cannot directly use that distance. You have to use this vector and figure out the gradient divided by the normal gradient. There's a expression for this because this value sometimes is negative. In the traditional one, it's always positive. That's why sometimes things goes weird. So at the end, you will have a deterministic formulation. Then you can solve problems like this. This is the original problem. At the end, on the right-hand side, you can see without the corrected formulation, sometimes it will fail. But with the modified formulation, you can find a reliable solution. Okay. Then I can show you a more complex problem. I think I have a nonlinear problem right here. This is a very popular math problem that was introduced in 2003, 21 years ago. So this area is the feasible space, and the solution is right here. So you're supposed to move this circle to this corner. So that circle will tangent to the red curve and the purple curve. And because the method I introduced was based on linear approximation. So the original shape of the constraint was nonlinear, but the reliability formulation are linear functions. So in the first iteration, there are approximations like this, and later on you can see the orientation of a constraint changes because in a new position, you will evaluate the gradient based on your new point. So that orientation changes. So at the end, that we were able to find that position so that this circular reliable region is tangent to the original constraint. So you have proper control of the failure rate. And if your initial guess is an infeasible point, using the old method, it will lead to incorrect solution. So with the modified approach that I presented in 2009, at the end you can find a solution right here, even though your initial point is an infeasible point. With a traditional one, it becomes a failure. Okay. So at the end, that's what I did for my PhD. I still have a little time. Let me show you something else. Okay. Let me turn off this. Let me find something. This way. So actually, in 2016, I published a paper, and in the paper, I introduced two different methods. Both methods was able to deal with non-normal distribution. Okay, and this paper was to show people how these two methods can be used and what's the difference between them. So that was my presentation. So for RBDO problems, this is the deterministic solution. If your design point is uncertain, there's a region for your uncertainty, and if you put it at your optimal solution, you have great failure rate. That's why you're looking for a shifted, safer probabilistic constraint. So when you move your solution onto the new constraint, your circular region will tangent to the original problem. So you can control your failure rate. That's the goal. But the issue is, usually you need to transform the distribution to standard normal space, like this. Like I said, right? You need to compute the shortest distance between the current position toward the failure region. This is a different method. I'm not going to cover it. So if one day you have a distribution that is unknown, then you cannot convert to standard normal space. So over here, I introduced two methods. One method is called is based on so-called Gaussian-based kernel density estimation. So on the lower right corner, there's a figure you can see. The blue curve is representing a PDF that is not normally distributed. So back in 1956 and 1962, these two gentlemen introduced how you can estimate the PDF based on the summation of a lot of normal distribution. So if you have a non-normal distribution, you can use this way to estimate the arbitrary shape. So that's what I did. You just have a multiple normal distribution and sum them up. That's the resultant distribution. That could be any shape. Okay? So, by this way, and with some math, similar to what I did, but it's a multiple Gaussian kernel, right? So graphically, you can see surrounding the mean value, you have some sampling points. At every sampling point, you put a small Gaussian kernel. You sum them up. That's your overall PDF. So it's like in the past, you are doing reliability analysis based on only one Gaussian kernel, Gaussian shape. But now you are dealing with multiple ones, and all the rest are very similar. So similar equations at the end, you can solve the problem. So I think I have some animation here. So I try to solve different problems. So over here, I created non-normally distributed shapes. And this is a hard shape. Even it's a hard shape, you can clearly see how this hard shape is located at a feasible space. Only only a small amount of this part is outside of the feasible region. And even for nonlinear constraints like this, if you want to take a closer look, I'll show you by zooming in. So in reality, if you have uncertain variables that is not normally distributed, this method can help. Okay. So over here, I believe every time when I randomly generate uncertain points, I usually generate a million points. So 1 million points that are randomly distributed in a particular shape. In my case, it's a hard shape. And I was able to control only a certain amount of those uncertain points that is outside of the safe region. So now you can control your reliability. Same situation for this particular problem, a different problem right here. Okay? And this paper even handles, talk about many different kinds of shapes. This is a hard shape. This is a very unique distribution, number 9. Number 9, it's a log normal distribution. Number 9, log normal. Number 3 is this is a uniform distribution, but within certain region. Even a weird shape like this, you can handle. This is a like. Okay. This one's so-called a normal uniform distribution. Uniformly distributed within x1 and x2. But this is a weird shape. I call this corona. And some others are known distribution. Like if you check statistical books, you will see this is one of them. 6 is uniform, 7 is log normal, 9 is Weibull, and 11 is Gumball. There's a distribution called Gumball. So no matter what kind of shape it is, you can solve it. Okay. So I don't expect you to work on this, but I just want you to know there are research problems like this. In reality, there will be uncertain variables. Sometimes it's not normally distributed, so you cannot transform to standard normal space. If you can, it's easier to handle. But if you cannot, you need very unique methods to handle it. So my method that was introduced in 2016 were some possible methods to deal with it. Okay, so I think that's enough for today. If one day you are interested in optimization with uncertainty, or if when you find a job in the future and you realize there's uncertainty and you just really need to solve this problem, you can always come back to me. I will try to help you. Because I don't think this is a lot for a graduate student to handle. It took me probably 1 year to figure out what's going on in RBDO. So like today, you saw I never use any notes, right? Because this is already embedded in my brain. I reviewed this I don't know how many times. So I was able to derive something that actually is quite complex and a little confusing. And I only actually covered the basics. I didn't cover the details, like what I introduced you this time in the PowerPoint. This is very complex. So only if in the future you need this, you can let me know, or check some of my previous research works. But I can tell you, by reading the paper, I don't think it's easy to understand. So that's why there's so little researchers in the world are working on this. Not so many. Now every time we go to conference, probably only every year, you only probably see 1 or 2 new methods. Sometimes you don't even see any new methods in that particular year. People just apply some existing methods to certain new problems. They don't develop new methods. So I rarely see new methods, because developing new methods in this field is very difficult. Okay? That's it for today. Okay, take it. All right.